We ended the previous lecture by defining the identity operator with a strange definition. Where K is some bases and we sum over all the vectors of the bases. We proved last time that this is the identity, and sometimes, perhaps I didn't use the notation, it's used as P. If you remember, which is the sum of K, P of K, which we defined in the previous lecture. Okay, why is that useful? Because it's extremely useful when we want to translate from one base to another. Let's see. Let's say I have some operator omega, and I use it on, actually not K, I don't want a basis vector, I want just some general base. Perhaps a bit stupid, but clearly can always multiply also by the identity. Can exchange them because I commutates with any operator, of course, and I can replace it by P. Again, nothing special. I'm allowed. I just write explicitly one definition of I.
L is any basis?
L is some basis. At the moment, I use the same basis
That you define.
that I define. It's just I'm summing over the basis, so calling it K, L, or something else doesn't matter. What's called in mathematics a mute index.
The point of this is to get to the eigenvectors as bases.
No, it's even simpler at the moment to show you that you can write any operator as a matrix.
Okay.
I said it, in some sense I've even shown it, but I want to reiterate it because it's central to what we're doing. any vector, I can write it as a sum over the amplitudes in a certain base. That's all I do. And what does appear here? This is a matrix times a vector. So if you want to write it down in the traditional way, you just write your U1, U2 till UN for the specific bases that I'm interested, the basis case that was defined in the beginning. And if I calculate, now I introduce a name that we'll use a lot, a matrix, the matrix elements of the operators, I have the matrix. Questions? It's important, so
Forgot the operator there in the big omega in the end.
oh, I just didn't write it down.
No, there. When it's purple.
Where?
Yeah.
So from here on, any time that you see such a structure, it's a matrix.
How we assume that this structure is matrix?
To prove that it's a matrix, go. So I'm looking on L. Okay. So let me be, in order to avoid confusion, I will look on a specific term, 1, 1. Doesn't matter, I can choose anything. Now, we know Because what an operator does, it takes a vector and maps it onto another vector, right? Nothing more, nothing less. Using an operator on a vector gives you a vector. And this vector, I can write it down as a function of any basis, and I'm choosing the basis in which I'm writing the 1 and 1. Okay? So, let me write down. Okay? Just wrote down the definition of the vector on which the operator operates. Our lovely delta function so it's a number. It's a scalar that fits to 1, 1. So I have an n by n set of numbers that I have to sum up in this way. That's a matrix.
It has to be a real matrix, not one on one. We need to do a sum. There.
No, it doesn't. At the moment, it doesn't have to be a real matrix. I do want it to be a square matrix. Why? Because otherwise, I'm not mapping into the same space. It's square. I haven't yet said that it's symmetric or hermetic. This will come later. Next. At the moment, it could be any square matrix. Questions at home? So we have a couple of people. Or non-conscious people. Okay. If you have questions at home, please ask. Good. So, since we said something about symmetric or Hermitian, let's define these terms. Okay, so any operator has a Hermitian conjugate operator which we write in the following way. The operator and a dagger. That's just mathematical notation. Still doesn't explain us what this operation of Hermitian conjugate does. Now, the definition is for any two vectors so for those of you who aren't steep in mathematical notation, it means that for each vector u and v, what I did here, I'm only emphasizing that after using operator omega on the vector v, I get some vectors that are right in the following way. The Hermitian conjugate works to the left instead of the right. And this must be equal. If for each pair of vectors u and v, using operator omega on v is equivalent to using operator omega dagger, the Hermitian conjugate, on u, omega dagger is the Hermitian conjugate of omega. A definition. Why is that useful? A bit of patience. So, if I go and remember how matrices work, okay. For each element L and K, I transpose the original matrix that represents the operator and complex conjugate. Why? So that's exactly what I'm doing here. Because when I'm doing this part first, after that I'm doing complex conjugate, right?
Right.
And because I'm operating to the left, I have to transpose the indexes.
It is the same as the adjoint, right?
In mathematics, it's also adjoint is with, if I remember correctly, the definition is without the conjugate, right?
Okay.
Or adjoint is just.
That will be the transpose, no?
Oh, that's. I'm not arguing. I don't remember the definition. In physics, it's Hermitian conjugate.
Okay.
So whether it's adjoint, transposed is definitely just this part.
Right. And adjoint. Yeah. Okay.
Okay, check it up and educate us in the next lecture. Okay, so that's a definition and we'll use it shortly. Okay, so at the moment I have all the language that I need in finite dimensional vectors and operators. except I still didn't define eigenvalues and eigenfunctions. But I would like now to stop here and move into continuous functions. Now we will quickly basically go back to all the definitions that we used before and use them for functions. What is the basic idea? The basic idea is well, if I have a vector, and excuse me if I'm playing a bit loose with the mathematical definitions. So I have a discrete number I, give me a discrete number, I'm giving you a value. That's a vector. It's part of the meaning of a vector. Now I want this I to be continuous. This does the same function unintended. X is some numbers that I feed into and ask what is the number I get for it. The only difference, this was discrete, natural numbers. This is any real number. The second thing I need, you probably paid attention that a lot of times we had a sum over I in different positions. Right. Sum becomes integral, again, because it's continuous. Now we're ready. So, what kind of things can I do with function? Start with all the things that I did for vectors, like doing addition, doing multiplication, all the things that we defined. So, I can sum up two functions. Gives me another function that I know exactly how to work. Scalar multiplication. You remember it was a sum over UI complex conjugate times VI. Okay, the sum becomes an integral. For each x, for each I multiply the values of the two functions, complex, and use a complex on the first.
The integral is over all space, right?
Yes, all space that is defined for my problems.
Right.
It's always continuous, otherwise use vectors. I can define, let's say, part of a space. It's always continuous. which will give us some mathematical headache at some point, but if you remember, we had a norm of a vector. Norm squared. Precise. Question?
This integral, if we put limits, is 1. Right?
If I force the norm to be 1, yes. If I think about it as a wave function, yes. If I just think here on operations on some field of functions, not necessarily.
It must be auto-normal.
Well,
If the integral would be 1, the two functions with the same.
just a moment, because I didn't yet define orthogonality. Orthogonality between two functions if this is fulfilled, psi1 and psi2 are orthogonal to each other. So we have a dictionary to all the things that we used for vectors. Okay. Now it's a good time to give some nice name. Any set of functions that fulfills all these conditions is defined
Space.
Hilbert space. Okay, so if you're doing quantum mechanics, endlessly you will hear some operator in Hilbert space or something along these lines. Okay, I said the word operator. So what does an operator do? Same as for vectors. I take an operator, I operate on a function, I get a different function. For example, X, we met it as an operator when we did averages of position. So that's easy. If you multiply a function by x, you get another function, which is the result of this operator. So, is any mathematical operation that moves you from one function to another an operator in Hilbert space? Wait a minute, because the operator can move you out of the space. So you have to see what it does exactly.
For example, it can ring the inner product, right?
Hmm?
It can ring the inner product, like blow it to infinity. So,
For example, if I want to define my Hilbert space that will fit physical use, meaning that it contains functions that could be normalized, meaning that their norm is always finite, and I use something like x squared here to infinity. No, it's out.
right.
So I have to be careful on the usage. Okay, we're interested in a subspace of operators. Linear operators, which basically mean if it's a scalar times a vector, I can use the operator on the vector, on the function, and multiply it by the scalar. If it's on a combination, I can operate on each one individually and then sum up.
The derivative and the integration are both examples, right?
I'll talk somewhat on derivatives shortly. Okay, before that I'll do A plus B and then do multiplication. A plus B. No problems. Order doesn't matter here. Convince yourself. On the other hand, don't have to be equal. Because, remember, operators are matrices, multiplication of matrices are non-commutative. We'll show shortly an example. Okay, not shortly, we'll show now. Let's look on two operators which we have already met. First we called the position operator, the second we called the momentum operator. Okay, so it's the definition. We have an additional term here. Therefore, AB is not equal to BA. Those two operators don't commute, and the order is important. We will see that this has very considerable physical effects. The fact that you can't measure position and momentum at the same time goes back to this fact. It's just a straight consequence of this fact.
I think there's a question in the. No, it's the.
The SEC.
Right.
Okay, questions just in voice, because if you have a question and write it down in chat, for those of you at home, no way, I can't follow it. Okay, so an additional trivial definition. It won't come as a huge surprise that the identity operator is the number 1.
In the case of matrix, is the identity matrix, right?
Right. So this is a case where writing down in continuous representation is shorter. Okay. So in general, if someone comes and writes down let's use B here. want to calculate it, go do the integral. Hermitian conjugate. Let's start with a specific example. What is the Hermitian conjugate of the operator x? X because x is not complex. Space is defined, any physical measurement is defined by something that's a real number. You sometimes, for convenience, combine x and y as a complex number, but that's convenience. The same things that you have for waves, that you represent them with complex numbers, but any measurable property of the wave is a real number. Okay, so just to prove it, well, prove is perhaps too big word for it. So if I'm remembering my definitions that psi1 x psi2 has to be equal to psi1 x that's a definition we gave half an hour ago. Just write down specifically. Okay, that's a definition of two that works on psi1. But since x is a real number, and therefore complex conjugate of x, Hermitian conjugate of x is x. Let's look on something that's a bit, well, and then you can generally, any function of x as the Hermitian conjugate is the same.
X means space, right? Any function.
If you want to call it p or
any physical.
Well, I didn't yet define what's a physical. At the moment, I'm looking at taking an operator x on a space that I'm defining my function and using it as an operator. Okay, now want to look on something a bit less trivial. Let's look on the operator. It's an operator. Yeah, we saw it with, this is the momentum up to minus IH bar. So, guesses, what will that be? Is it the Hermitian conjugate of itself?
No.
As X? No. Let's see. A bit surprising, but let's see. Okay. Let's for a moment assume that, you know what, let's not assume anything, let's start from here. We have our good old friend integration by parts. Let's assume for a moment that the integration is over all space.
It's going to be the convergent, the psi 1 stuff.
Indeed. But since it's zero, why is this zero?
Because the wave function needs to go
To be
zero.
normalized for any problem in quantum mechanics, I have to be able to normalize it. So it has to go to zero at infinity. So this contribution is zero. So therefore, although specifically you're right, psi 1 has to be conjugate, but since it goes to zero, so I don't care about it. And that's the second term in the integration by parts.
So it's the negative of the one above, right?
Because though to do X has no imaginary part, so you can put it within the complex conjugate, within the complex operator. And clearly, the complex conjugate of minus the, meaning that it's not Hermitian. Dot to the x is not Hermitian. I want to turn it into Hermitian. How do I do it?
Multiplying by I.
Exactly, I multiply it by I. If I multiply it by I, then I get x conjugate is equal to I. Going through the same steps. But here, if I want to put the complex conjugate on everything, I have to put here minus. Minus times minus is plus. So, to all of you who were amazed to see in the Schrödinger equation I do to the t, it has to be an I because energy is a physical operator. And now I'm stating something, any physical operator is an Hermitian operator. That's why we have these i's before the derivatives according to x or t. Now, why is that true? That has to do with the eigenvalues of these operators. Now, some general statements on Hermitian operators. So Hermitian operators we have a couple of Hermitian operators. Then their sum is also a Hermitian operator. This comes out from the fact that they're linear. Another trivial statement. Where lambda is a scalar.
And it can be complex, right?
A real scalar. Can't be.
Can be complex. It could be.
It's only real. So write it specifically. Where the operators in the red squares are Hermitian. Convince yourself.
It's like the symmetric and
Anti-symmetric. It's still, the sum is not Hermitian because of this I here. But if I'm just looking on the two operators that are in the red boxes, these two operators are Hermitian. You can easily convince yourself that the sum is equal to 8.
Why there is an I here and the I cannot be cancelled?
Because what do I do here? It's actually a non-statement, but we'll use it in a couple of lectures. You cancel the I, you sum up, you get A, right?
Yes.
That first of all has to be, because this is equal to this sum, right? But the guys, the operators in the red boxes are two Hermitian operators. Okay, why sum? So it's A dagger.
Yes.
That you can always transpose them because it's a summation. Here, what happens, the I becomes minus I, again, everything is good, right? So, Here is the whole thing that changes it into a non-Hermitian operator. Because of this I, the sum here is a non-Hermitian operator.
Because lambda has to be E.
It's not lambda, it's because if you'll do here you have something that's not Hermitian, the summation of it.
Of course, if A is Hermitian, for example,
If A
the
is
second term
Hermitian, so
vanishes,
life
and-
is good.
Right.
Why? Because then this is 0 and all's good. And this plus this is just twice the operator divided by 2. So this term is not in the game, no problem. Okay, the Hermitian conjugate of so the multiplication of two Hermitian operators is not necessarily Hermitian. When is it Hermitian? If A times B is equal to B times A, then you can swap it and all's good. But it's not necessarily true. So we got to the main mathematical point of this whole course, eigenvalues and eigenvectors. I think it's a good point to take a break of a quarter of an hour, and we'll get back. 15-20 minutes, we'll define everything that has to do with this, and then we can do the basic assumptions of quantum mechanics. Eigenvalues and eigenvectors of linear operators. So the definition is very simple. If I have an operator A and it operates on a wave function or a vector, whatever you want to call it, psi, and gives you the same psi multiplied by some scalar, that's an eigen. The scalar is the eigenvalue. and psi is the eigenvector. Okay, usually denoted by psi lambda, the eigenvector belonging to the eigenvalue lambda. Why is this strange combination of German and English? I don't know. Can check it up and try to come with an explanation. How that everything is German makes sense because all this theory was developed in Germany. Why it was translated into English in a half form of that I don't know. Okay. Properties. Extremely important. All eigenvalues of an Hermitian operators are real. From here is a jump to any operator that represents a measurable physical quantity has to be Hermitian is clear. Someone gives you an operator which he claims can be measured and it's not Hermitian, it's wrong. Another thing that we know about eigenvalues and eigenvectors. Eigenvectors belonging to different eigenvalues are orthogonal. Two very strong statements. And actually I'll prove them both in one step. Let's take some operator A, operate on the function psi1, and this function is an eigenvector with an eigenvalue lambda 1. Let me operate with the same operator on some eigenvector psi2 with some eigenvalue lambda 2. Okay, so psi1 and psi2 are both eigenvectors of operator A. I'm taking this equation and multiplying it by psi2 complex conjugate. I'm allowed to do it. Why am I allowed to do it? Because A is Hermitian. To what is this equal? Remember, A is Hermitian. Zero. But just by the definitions that A is Hermitian. Let me write down explicitly what's written here.
This is the properties or the proof?
This is the proof of these two statements. They're actually proved at the same time.
Why do you think that?
Because that's the definition of this symbol.
Ah.
You see a matrix element, it's either a sum if you are in a discrete case, it's an integral if. Remember, you have to end up with a scalar, a number. The only way to end up with a number from function is either a sum or an integral. Okay, I just wrote it down explicitly. Now I look on what's written here. This guy is this guy. This guy is this guy. And this is this. So what do we have here? We have here lambda 1 minus lambda 2 complex conjugate. One. That's just what's written there. And all this has to be equal 0. If I'm considering psi 1 and psi 2 that belong to two different eigenvalues, the only way that this can happen
Is that the integral is 0?
is that this is 0 orthogonal. If psi 1 and psi 2 belong to different eigenvalues, they must be orthogonal. Otherwise, this part is not fulfilled.
And
If it's the same case, meaning psi 1 and psi 2 belong to the same eigenvalue, and let's take it even simpler. Psi 2 is psi 1. If psi 2 is psi 1, this is 1.
So lambda 1 minus lambda.
So if it has an imaginary component, it doesn't go to 0.
right.
So the only way that it can be fulfilled is so we hit two birds with one stone. Finished. We proved these two statements. Okay, what happens when I have two or more eigenfunctions that belong to the same eigenvalue?
This is the generator.
This is the base.
I didn't say the word base, that will come further on. No, I'm asking, let's assume I have two functions, psi 1, psi 2, that both of them belong to the same eigenvalue. They are not just a trivial multiplication by a constant. Can happen. That's known as degeneracy. And then you can construct an orthogonal basis of this degenerate sector using Gram-Schmidt. We won't use it in this semester. Next semester, when you'll learn about degenerate perturbation theory, it will be very important. So just remember it. So we have here something that smells like a basis, right? I have eigenvectors of an operator that are orthogonal to each other. That's almost a definition of a basis. It is a basis. If we have degeneracy, so use Gram-Schmidt to finish up. Now, this one I won't prove, I'll just state. This is a full base, the eigenvectors of a Hermitian operator are a full base, and they span any function that belongs to this Hilbert space. So when we discussed that we can write down a basis of the space for 1 till n if it's discrete. Continuous case if it's not discrete. We can also write a basis of all the eigenvalues that spans the whole base, and any vector in this space can be written as a sum over all the eigenvalues as the same way as we used any base that we previously defined. As good as a base as any other base.
This is in the sense K.
Good.
It's lambda.
Lambda.
Now we say lambda psi, and then what?
I have, for each eigenvalue, I have an eigenfunction, so I sum over all the eigenvalues, multiply them, scalar multiplication of the vector, multiplied by the eigenvectors, and this is a description of a vector u in this basis. The only thing that I just stated didn't prove that it spans in, it's a full basis and it spans. See, if someone is interested, you can go back to your linear algebra course. I hope that was proven there. Okay. Basically, the next 20 minutes, half hour, will be the whole content of the course. All the rest and any other quantum mechanics course that you'll ever do map to this statement, nothing changes. That's the basis of quantum mechanics. Everything else is examples. postulates of quantum mechanics. All you can know about a physical system is contained in its wave function. Nothing more, nothing less. There's no information outside the wave function. Everything is within the wave function, and you'd have to do some mathematical manipulation in order to pull out this physical information. You have something that you can't pull out of the wave function, you can't do it. That's a full physical description. You want to know the result of some measurement, you have to connect it to an operator, which is linear and Hermitian, and that's the quantity you have to use on the wave function. As we said, this actually forces you that this operator has a basis, and any wave function could be described by this basis. Now the bombshell. Till here, more or less, you got used to in the first few lectures. We took wave functions, we calculated averages of or variances of physical quantities. This is summed up in these two statements. And now comes something very unexpected. You can't measure anything that is not an eigenvalue of omega. What we did till now are averages, but this is a much stronger statement. Your measuring device can give you only results that are eigenvalues of.
So if you in the quiz give me a measurement and ask me if it's possible, I need to check if it's eigenvalue of the operator.
Right. If it's not an eigenvalue, that's not something you could have measured. Let's say if you have a situation where you have, let's consider a spin half, has two possible measurements.
Spin of what?
Spin up and spin down.
Spin up and spin down. I'm discussing it in the clips several times. I will discuss it, I think, in next lecture in more details. But at the moment, if I have some physical quantities that can come up only up and down for some reason, you can't measure out of it zero. You can measure an average zero. What does it mean? You will repeat the measurement time after time after time, you'll get zero. But in each particular measurement, you'll see either up or down. If you want, it's the things that I talked about a lot in the clip. Position has eigenvalues. We will show them specific positions. Therefore, when you measure where a particle hits a screen, you measure it here or here or here or here, you calculate the probability, you get the wave function square. You perform the measurement at a particular point. And that's hidden in this statement, which is very, very, very unintuitive. So, let me give you another example. Probably in your modern physics or introduction to quantum mechanics or whatever course you did, you learned that you have energy levels, right? You find the system only at certain energy levels.
So the energy level is the eigenvalues.
The energy levels are the eigenvalues.
Eigenvalues.
A system could be in a superposition and the average energy could be anything. But if you measure the energy, it could be only in one of these eigenvalues. And as I say, very non-intuitive. Okay, so Okay, I know that I measure one of the eigenvalues, but what is the probability if I repeat the experiment again and again and again and again? What is the probability of measuring a specific eigenvalue? Take your wave function. Write it down in the basis of the eigenvectors of this operator. Take the amplitude, square it, and that's a probability.
Why did? Okay.
You know that the sum of all these things squared has to be 1, because it's a basis.
I assume it also from Gramsci. We did there, we get the open normal base.
Right.
The last postulate was the Born rule, right?
Mm-hmm. You actually met it. We said the probability is psi squared. Sure, I just have to. I didn't give you what are the eigenvalues and the eigenvectors of the position operator yet. That we discussed a lot. Until now, all these postulates describe the situation. Someone comes and gives you a wave function and asks you what can you measure and what is the probability of measuring any physical quantity. You have to pull out the operator. And once you pull out the operator and know its basis and eigenvalues, you can answer for a given wave function anything that you're asked about. It could be complicated mathematically, but at the end of the day, it's a very simple procedure. How do I see that well, let's assume that I knew the wave function at time t. What can I say about the wave function at time t? Well, here comes in Schrodinger's equation. And basically, in a very concise way, the energy operator times psi has to be equal to the Hamiltonian operator times side. And if I give you t0, I can take it to any time t. So I have to have initial conditions, know the Hamiltonian. We'll spend a lot of time of solving this type of equation, but in principle, that's all we have to do. Nothing more, nothing less. These are the 5 basic postulates of quantum mechanics. That's all you have. You have to know the wave function at a given initial condition, know how it develops in time, pull out the answers to any physical question you want to answer. Nothing more, nothing less. Now, the 6th postulate, which is the Copenhagen picture, this is not necessarily part of quantum mechanics, it's under discussion, but for any operational way of working with quantum mechanics, it's very, very convenient. Because all other descriptions throw you into all kinds of problems. Again, I speak about it in the clips. You can see it's an open question. You have the Copenhagen interpretation. You have the many-worlded interpretation. You have Bohmian mechanics. You have a salad of all of these ingredients as different combinations. But in the end of the day, to answer anything that you'll run into during your undergraduate and graduate student studies, Copenhagen interpretation, although it has its problems, gives you a very clear definition how to work out the problems. Okay, so as I said several times in the clips, and I'll repeat it here, Feynman's advice, shut up and calculate. Don't worry about the philosophy, although it could be interesting, certainly very interesting, but in order to be able to do some predictions with quantum mechanics, you don't need. So what is the Copenhagen interpretation? It's a very simple statement. Tells you, let's say I perform a measurement of omega time t. Okay, I had some wave function, not necessarily in the base of the operator that I measure.
This is psi t, not theta, right?
No, it's t.
It's theta.
Because this is before. How it develops with time, I know. Give me a time where I have the initial conditions. We'll see that for stationary case it's very simple. So everything's good. I did a measurement. According to 3 time t I measured some value omega lambda, or lambda if you want. Right? That means all the other components die out because I measured that it's at state psi lambda with probability 1. Therefore, I don't write here any scalar because it's 1. I know, I measured it in lambda. That's known as the wave function collapse. It was previously made out of all kinds of superposition of components. I measured. Becomes psi lambda. You note that it's extremely strange.
There is some kind of information lost, right? There?
No, there are 2 basic problems with it. One is what the dynamics of the system. You gave me a dynamics which is linear.
Right, and suddenly you broke.
And suddenly, at the point of measurement, it became nonlinear. At the moment of measurement, all components disappeared. That's not a linear operation.
Right.
I claim that everything is Hermitian linear operators, but measurement is definitely not.
Right.
It's just the place, the scalar. It's not linear.
It's not. It's not linear because it's procedures that you can't write down as some matrix times the thing. So you have 2 types of measurements here, of development with time. Schrodinger's, as long as you don't perform a measurement, and some nonlinear, which is known as wave function collapse at the point of measurement. This hybrid behavior is strange. Moreover, yes.
It's also non-relativistic, right? There's
No, but it has a huge problem. It is relativistic. Let me give me a couple of minutes. This is the point of that makes understanding quantum mechanics close to impossible, if not impossible, because it works wonderfully. It makes sense in the meaning I measured. And how that happens? Now, 2 points. One that you said, but I want to go a step before it. I said measured. What is a measurement? Well, is it,
It's to observe.
yeah, but, okay. What it means in reality, very clear. I take an apparatus, like what I explained in my clips. You look on a screen, see, you have a camera, it sees a point, that's a measurement. Yeah, but is the measurement the fact that the computer recorded the point? Is it that a conscious being looked at the point? Is it any being? Einstein went nuts about this point. He said, I refuse to believe that a mouse can change the universe by staring at it. But that's what it says. All these are very vague and ill-defined. What is measurement? How do I perform a measurement? Who has to measure?
And also, how does the entanglement works?
Entanglement is a whole different can of worms, but I'll give you a very simple example of your question about relativistic effects. Let's say I have a particle that is either here or on the moon. Could be. Let's simplify our life and say we have two positions, here on the moon. That are the two only positions I can measure with my measuring device that has an operator and so on. I'm measuring here. And I see there is a particle. I can guarantee that if someone sits on the moon, at t plus epsilon, he won't measure the particles there. How long is that epsilon? Well, relativistically, it seems that it has to be at the speed of light because information has to pass there. The answer is no, immediately. Doesn't matter if he's on the moon or on Alpha Centauri or in Andromeda's galaxy. Instantaneously, he loses because I know that it's here. Now you can tell me when I pass information quicker than the speed of light. The answer is no information passes because I can't create with this a communication device. Communication you can do only in the speed of light. Killing components of the wave function elsewhere, you're doing instantaneously. People try to create paradoxes with that. No, that's not the paradox. It works with relativity. Fine. The problem with relativity, at least with the versions that we have here, is that
it's non-Lorentzian variant.
Your time development here is non-relativistic, but change it to the Dirac equation. As I said, the same principle continues to work here. So even if you write a relativistic entanglement and really not, I have a few clips that are now should go on the site within the next few days that talk about Bell inequality, which is also a form of entanglement really. That tells you that if you have two particles that, let's say, have to be spin up and spin down, if I measure this up, I force the other one to be down because that's one component of the wave function.
Right.
That's intended.
To conserve spin, right?
For example. So, okay, so the Copenhagen interpretation is forget all your problems. Measurement is what is defined in the quiz as a measurement. And that is what happens at the measurement. Now, you want to continue the development of time? No problem. Take this guy, stick it back as an initial condition of the Schrödinger equation. Work. You'll have it at the times that comes after the measurement. Perform another measurement, same procedure. What did you measure? What is the wave function, the eigenvector that is appropriate for that measurement? That's the initial condition. Stick it into the Schrödinger equation. Go on. That's it. That's all you have. Just for a taste, we thought to go into all the what does the many world interpretation say? Excuse me, you performed here a sin of dividing a quantum particle and a non-quantum observer. Stick them both into a global wave function, and you'll find that for any measurement there's correlation with the wave function of the measuring device. So for each measurement you'll get a new component of the wave function. So in this case you're consistent, but your wave function continues to split on and on and on and on. And on one hand, it saves you all this mumbo jumbo about a non-continuous measurement and so on. On the other hand, it completely doesn't fit our objective feeling about how the world works. We're not feeling that we split on and on and on and on. There was a measurement, we saw a result, we know that's the result. And the many waves tells you, okay, your consciousness splits to all the different. So if you're happy with an infinite version of yourself going on and you are just one of them and all others continue to live, you have no communication with it, you know nothing about it. Well, that's your philosophy. As I said, shut up and calculate. Calculation doesn't make any difference. Now, people tried to come up with some measurable difference between those two interpretations. Until now, there's none. So, as I said, quantum mechanics, from the point of view of an algorithm, very, very simple. Take your wave function, use Schrödinger equation. Ask yourself what you want to measure. Calculate the eigenvalues and eigenfunctions. Write your wave function in the basis of this operator, and you can answer any questions that someone asks you about it. Now it becomes a mathematical challenge if the system is complicated, if the Schrödinger equation is complicated, so on and so forth. But from the point of view of algorithms, that's all. Identify your wave function, development in time is here. Identify what are the interesting values that you want to measure, calculate the eigenvalues of the operator. That's it. And basically, we'll start in the next lecture from the simplest kind of system that one can think of it, which is the spin, and see what is the consequences of using this type of behavior. Okay, so questions at home here? We're taking over this external entity.
Thank you. Thank you.